Greetings, I'm Mike Grontman. This video clip demonstrates rotation of Apsides caused by Earth ablateness. The coefficient J2 in the expansion of the Earth's gravitational potential describes this most pronounced deviation from spherical symmetry of the shape of our planet and of its mass distribution. More video clips illustrating other effects of interest to space mission design and to spacecraft design can be found at the website astronauticsnow.com. The simulations are performed using AGI's STK. This video clip demonstrates rotation of the line of Apsides caused by non-zero J2. The simulation covers 2 months. The orbits in our example are elliptical with a period of 12 hours, perigee altitude 500 km and apogee altitude 39,867 km. Inclinations of the shown 3 orbits are 0 degree, purple color orbit, 90 degrees, white orbit, and 63.4 degrees, light brown. The latter orbit is a typical 12-hour Molniya orbit. The argument of perigee of all orbits is 270 degrees. The red vector facing you is the vernal equinox vector. Another red vector points north and coincides with the Earth's rotation axis. The Sun is on the left, illuminating the Earth. The yellow band on the surface is the equator. The generic name for perigee and apogee are periapsis and apoapsis respectively. The line connecting periapsis and apoapsis, in our case perigee and apogee, is known as the line of Apsides. You can also see 3 apogee vectors, that is, the vectors pointing from the Earth to apogees of the orbits. The vectors are color-coded as their respective orbits. Note the moon that would appear moving from top right to left in the background. Earth ablateness or non-zero J2 causes changes in the direction of the lines of Apsides, the effect known as rotation of Apsides. Apogee vectors help to visualize rotation of Apsides as the change in the direction of the vectors is clearly seen with respect to the coordinate grid. If the Earth were perfectly symmetric, the orbital plane would have remained fixed in inertial space. In addition, orientation of the elliptical orbit with respect to the orbital plane would have remained constant. The Earth ablateness causes rotation of Apsides. For a polar orbit, for example, this effect would move, in time, the orbit apogee from the northern hemisphere to the southern hemisphere. The rate of rotation of the line of Apsides depends on orbit's semi-major axis, eccentricity, and inclination. One can see that the equatorial, purple orbit and the polar, white orbit show rotation of Apsides. In contrast, the line of Apsides of the brown orbit does not rotate. There are 2 orbit inclinations, approximately 63.4 degrees and 116.6 degrees, with 0 rotation of Apsides. Perigee and apogee of such orbits would preserve their orientation in the orbital plane. Such orbits are known as Molniya orbits, favored by many communications satellites serving polar regions of the globe. Note that geostationary satellites are unsuitable for communications with the polar regions. The brown orbit in our example is a 12-hour Molniya orbit with inclination 63.4 degrees. In our simulations, the lines of Apsides rotate by 5 and 10 degrees for polar and equatorial orbits respectively in 1 month. Note the moon moving from top right to left in the background. The rotation rate of the line of Apsides is actually twice faster for the equatorial orbit, but it is counterbalanced in part by rotation of the line of nodes of the orbit in the opposite direction. We began our simulations with apogee of the white polar orbit located exactly over the North Pole. In 3 years, apogee would reach the point exactly over the South Pole. At the same time, the line of Apsides of the equatorial orbit would complete 1 full rotation around the Earth. More video clips illustrating other effects of interest to space mission design and to spacecraft design can be found at the website astronauticsnow.com. Thank you for watching. I am Mike Grontman.